All right, hello once again. This is Dr. Jones, and this is a lecture on the second part of recursion from chapter 18. This will be a short lecture. We're just going to talk about how recursion can be used to solve some of the more basic problems where recursion is designed to actually be a better solution compared to the alternative iterative implementation that we learned way back in 2301. So the first problem is the Fibonacci series. And the Fibonacci, if you guys are familiar with some of the things you're learning in your math classes, the Fibonacci series is where we add two numbers where the sum is the sum of the previous two. So as you can see, let's start, 1 plus 0 is 1. And then when we get to the 2, then we add 1 plus 1. That gives us the 2. Then we get to the 3, then it's 3 plus 2, that gives us the 5, then the 5 plus 3, that gives us the 8, so forth and so forth. Now, interestingly enough, the Fibonacci series was originally conceived to represent the growth rate of a rabbit population. Now, this was an idealized rabbit population, but I guess Mr. Fibonacci had a lot of time on his hands to study and explore how rabbits grew over time. Now, the equation at the bottom of the slide is pretty much all we need. Anytime we get to have an equation, then we can pretty much say our design is 95 to 99% complete. So in this case, the new number, which is f sub n, where n is the index, is going to equal f what it was 2 indexes ago plus what it was at the previous index. So this slide is showing you how to do this with recursion. Now, what I did in my primary section, I had the students actually do this without recursion and to try to compare how we would do it. I don't have that here, but as you guys can see, this is the Fibonacci series using a recursive method. We pass in the index, and we have two base classes. All right, so we're checking to see if we are at that base class. If we are, then we're going to return a 0 if the index is 0, and we'll return a 1 if the index is 1. Now, the Fibonacci is a very interesting kind of recursion problem because, as you guys can see, when we're not at the base class, we are actually doing two recursive calls. So when we solve the Fibonacci series utilizing recursion technique, we're breaking this up in two problems. Okay, the first one is this recursive call, and then the second one is the other recursive call. And each recursive call, we're looking to see where we are in regards to the index. If we are not at the index, then we just continue to push it down till we get to that base state. The author of the book wants you to think recursively in almost any way, any situation, and it would help to understand how recursion is done. So he has an example where he asks us to drink coffee, and this could be drink coffee, it could be drink soda, water. So let's see, if we're drinking these things, if the cup is not empty, then we take a sip, and then we repeat steps 1 and 2. So it's pretty straightforward, pretty simple. And then, so this is the step-by-step process on how I drink anything that's of liquid form. And inside, if I were to represent this recursively, then here it is. I have an if statement, and I'm checking my I'm checking the non-base class. So if the cup is not empty, meaning the cup being empty is the base state. So if the cup is not empty, then we're going to take one sip, and then we just continue to do the recursive process. Now, in this case, we don't have that else to do something else. In the way we implement it, we don't need to do that. And basically because we're not returning anything. If we were to return something, then more than likely we would probably have an else there. But it all depends on how you want to set up your recursive method. You just need to understand the main components. The first one is the method. Know what we're going to return, if we're going to return anything, and what we're going to pass in. Then we need to know how can we check a conditional statement that checks our base state. And then if we're not at that base state, we do something, and then we make a recursive call, and when we make this recursive call, when we invoke this recursive call, we have decremented our variable or object so that it gets closer and closer to the base state. That's the basic structure of any recursion method. Look at another one, and this is file searching, where we want to get the list of files from a parent directory. For each file that's inside the parent directory, we want to count the size of that file. Now, if the file is a subdirectory, we want to repeat the same process. So we want to know how big the folder is in regards to how much memory it takes up. And we do that by counting the size of each file, including the size of the files in any subdirectory. So if we want to do this recursively, it's going to look something like this, where we have a method called getSize. We're passing the file. In this case, because we care about, we want to know what the size is, we're going to return a long. And we're returning a long rather than an int because we expect this number to get pretty big, especially if there's a lot of files in the folder. So we first initialize our size, which we'll return later on. And then we're going to check to see if the file is a directory. If the file is a directory, this is where we do a recursive call. So we have to get all the files in that subfolder. And then for each of those files, we are going to call getSize again, and we're passing in that particular file. So we go back in here, and then we check to see if that's a directory. If it is, we do the same process until we get to a file. And once we're at a file, this is where our base class is. Then we say the size is just going to be file.length. And once we get here, we can now return size. So this is how a recursive method would be done. And I'm looking at this, and this actually would have a compile error, and I apologize for that. We're missing the other brace that sits outside for this if statement. So there should be a brace here, and before the else, there should be a brace, a right brace that closes this off. But this is also in the book, and I probably just copied it down wrong, so my bad for that. But that's how we would do recursion for getting the file size, the size of files inside a particular folder. The last thing the book talks about is tail recursion. And tail recursion is a special kind of recursion, and it's on the left side of this slide. So tail recursion says we make our recursive call at the very end of our method. So as you guys can see here, I have this method, and we're doing executing statements, statement 1, statement 2, statement 3, all the way down, and then we will call ourselves and decrement I. So of course we have some type of conditional statements going on here as well, but we're going to decrement I, and this is our recursive call. And because this is the last statement, this is called a tail recursion. Now in a non-tailed recursion, which is what we've been doing up until now, a non-tail says we make the recursive call anywhere but the last statement. So in this case, I have statement 1, statement 2. I make my recursive call, and then I can also have other statements as well. So this is something the book mentions, because if you're dealing with recursion, if you guys recall from part 1, a recursive method is a performance hit on any program, because every time you're making that recursive call, you're adding variables to the stack. So all the variables you have in this method, they will get not reallocated, but a new stack will appear, a new section on the stack will appear for the space for these variables. And this is why it's a performance hit. Now, in the case of, when we compare that to an iterative loop, we're not creating new variables over and over and over again. And that way, iteration is a much better performance, has better performance compared to recursion. But if we want to use recursion, and there's going to be cases where recursion is the most appropriate solution, then what we try to do is come up with a tail recursion, because a tail recursion, in theory, would not be as big as a performance hit as a non-tail recursion. So what the book and what the author is trying to get you to understand is what a tail recursion is, and a tail recursion is simply the last line of the method is our recursive call, and compare that to a non-tail recursion where the recursive call happens anywhere other than the last line. And the whole purpose of it is a tail recursion has better performance compared to a non-tail recursion. But they still both aren't as efficient compared to an iterative loop. So make sure you understand that. Now that will conclude this lecture, and hopefully you guys be ready